you see the full screen of my presentation?
Yeah.
Okay, thank you very much. So hi to all the attendees. My name is Bassel Youzkatli, and I will be presenting the topic about multiphysics analysis for high-power dielectric devices. Basically, my presentation will be divided into three parts. There will be an introduction and a conclusion, and between those two parts, there will be the main discussion of the main topic, which is the multiphysics analysis. So first, to start, let's set the context of this topic. So it's basically related to the PhD projects, for which the main objectives, in my case, it's to optimize the power handling of high power components for future generation of European satellites. This includes increasing the power breakdown threshold for multipaction and corona, and also increasing the thermal and structural robustness of the high power devices. So one of the targeted examples is multiplexers, which are designed to physically isolate high power transmitting channels in satellite payloads. So those type of components have a lot of challenges and trade-offs, such as respecting a very high rejection between adjacent frequency passbands, having low RF losses, being compact, and of course have high dissipation and conduction of RF losses induced heat. So one of the solutions that is proposed in the literature to and also in the industry, actually, to solve this kind of problems is to use dielectric resonator filters. So in this topic, we'll be doing RF thermal coupled multiphysics analysis on this type of devices in order to find the optimal trade-off between the dielectric loss and the thermal conductivity of the dielectrics in order to minimize the ohmic losses and the heat buildup inside the structure. The structure that we'll be considering in my study is a very simple cavity consisting of a metallic body in which is incorporated a ceramic puck or resonator and a spacer or support for the ceramic. So the casing is an aluminum casing, and it's silver plated in order to have to minimize the surface losses. And the electric resonator and the spacer, for the purpose of this study, they are made of the same material, and we suppose that those two components will have a fixed permittivity of 9.2, which is very similar to what we have with alumina. And even though that will be changing the type of ceramic, we'll consider this permittivity fixed just to observe actually the results at the same resonating frequency, which is in our case 12.5 gigahertz. So why did I use this configuration? Well, basically because it's the basic constructing element of filters and multiplexers, high power filters and multiplexers. It's simple to model and simulate. It's also simple to fabricate and test. And also it's a reference structure broadly documented in literature. Sorry. So for this structure, we will consider the fundamental mode, which is the TE01 delta mode. So for which the electric field is circular and it is concentrated in the dielectric pack, and the electromagnetic field is perpendicular to the electric field, of course, and it forms a kind of magnetic loop inside the structure. Magnetic dipole inside the structure. So before discussing in details the analysis, let's take a look quick look actually on how actually the literature handled this kind of problems and how it addressed the power handling problems from multiphysics point of view, and what are the solutions and the problems that were encountered. So here, for example, we have an example of of a structure that was proposed, for which they use they didn't use actually the fundamental mode, but they used a higher order mode, the degenerate mode, for which the power, the dissipated power, actually 90% of it is located on the surface of the resonator, which means actually the metallic enclosure, which in this case is very appropriate for optimal heat evacuation. So we can see in this case that for actually ambient temperature of 75 degrees, the device reached a temperature of around 81 degrees when it was injected with a 120 watt input power. In another example, actually, they address the problems that we can face with the dielectric resonator filters. Here, for example, they consider a structure for which they are using the fundamental mode, and they are using a very high dielectric ceramics. So in this structure, when they inject 210 watts of power, they noticed in simulation that those ceramics can reach a very high temperature of 100,000 degrees, and it's basically due to the high loss of those ceramics, and also to their low thermal conductivity. So now we'll go back to the analysis. As you may know, there are different types of ceramics available in the market that can be used for this type of filters. In our case, we will be selecting mainly two types of ceramics, alumina, and the second type is aluminum nitride. Why? Because mainly actually because of the expertise of the ESR lab at University of Limoges in developing these types of ceramics for RF applications. And this actually goes in adequation with the TESLA project objective, which is to rely on European developed products and solutions. And it also responds to the aim of the study in covering large scale of dielectric losses and thermal conductivities. This will allow us to narrow the selection of ceramics that will satisfy the requirements that we are looking for in terms of power handling. So here, okay, we can see that the alumina will have a very low loss, very low thermal conductivity, and the aluminum nitride will have a high loss, high thermal conductivity. For our analysis, we are considering 3 cases. The case number 1 is alumina, and it's a very low loss. It has a very low loss, and which is actually good RF-wise, but it also have a low thermal conductivity, and this can be problematic. It will depend on how the analysis will tell us, what the analysis will tell us. And the second case is alumina, that with properties that represent what we can find in the market actually. So it's usually the alumina has a high loss, but also it has a very high conductivity. So it's 170. Like if you compare it to the aluminum, metallic aluminum, it has 237 watt per meter Kelvin conductivity. So it's a relatively high conductivity. And case number 3 that we consider is an alumina that is developed internally also at the ESR, like the alumina actually in the case 1. So this aluminum nitride has a kind of intermediate properties between case 1 and case 2. So what is the multiphysics analysis method used in our case? So actually, to summarize, usually there is an exhaustive study that is done for this type of problematics, and it involves an iterative loop of 3 steps. So first we have our model. We design it in the electromagnetic domain, and we make some will have a high temperature due to the power high power injection. So excitation, sorry, high power excitation. So we made the variable the conductivity of metals, permittivity, and the electric loss tangent of dielectrics. And so once we analyze this model, we will put it through the thermal analysis, in which also we'll have variables such as thermal conductivity and emissivity. And in our case, we'll consider for space application, we need to consider all type of heat exchanges, which in this case are like conduction and radiation. So once the thermal analysis is done, the results will be injected into the structural model, so that because for each material they will have each material will have its own coefficient of thermal expansion. So due to the thermal change, the device, all the different materials composing the device will have their physical dimension changed. And this will be done in the structural analysis. And also, if we include some tuning features, those tuning features will be modified into this structure. And then at the end of this analysis, a new geometry will be generated and will be injected again into the electromagnetic model. And the analysis of the electromagnetic model will tell us if what we obtain as a result is enough or not, or if it does satisfy the requirement or not. Otherwise, we will continue the loop and optimize the structure. And basically, the output parameters we are looking for are the S parameters, the losses, the temperature maps, also the mechanical deformation. Now, if we go back to our case, which is to determine the effect of dielectric loss of the dielectric and thermal conductivity of the dielectric in the behavior of the device in terms of thermal performance, and power handling performance, actually. So in this case, we'll make a very simplified study that uses unidirectional coupling using CST's thermal steady state solver. So this method involves two steps, which are doing electromagnetic analysis and then doing a thermal analysis, in which we inject the losses that were obtained in the electromagnetic model. And for those two analyses, we can consider all the parameters that are fixed, the one that we discussed earlier that we said that will be variable. In this case, we can consider them as fixed parameters. And then, at the end, we will have S parameters and the temperature map of the device itself, which will allow us to conclude on the thermal behavior and the effect of dielectric losses and thermal conductivity. So for all the following analysis that we'll be seeing, we'll be considering an ambient temperature of 75 degrees Celsius, which corresponds usually to the thermal constraints that we have on satellite payloads. So with the first example, we can see that this example actually corresponds to the alumina that has a very low loss and also low thermal conductivity. We can see that only 1% of the power is lost within the structure, and 54% of this power is lost in the volume in what we call volume losses, which are actually here the dielectric materials. So the two pieces of ceramics that we saw earlier in the model. So here we can see that in this case, the maximum temperature is in the dielectric path, and it reached 117 degrees Celsius, while the cavity, the metallic cavity, the hottest point in the metallic cavity reaches 77 degrees Celsius. Now, when we look at the case number 2, we can see that this one has the highest losses in our three cases. So it has over it's almost 7.6 watts that are lost within the structure, which represent actually 7.6% of the excited or the injected power into the structure. And so 94% of this lost power is actually lost in the ceramic parts. So for this case, also we have a maximum temperature of 158 degrees Celsius. So now, if you move to the case number 3, which is an intermediate case, so we can see that we have more than 3.6% of the injected power that is lost within the structure, and 88% of this lost power is lost within the ceramic part. So for this case, we have a temperature of 157 degrees that is reached in the ceramic pack, and an 85 degrees that is reached in the metallic cavity. So there is a summary of the three cases. We can see that case 2 and case 3 have a very similar temperature behavior for the ceramics, and the case 1 is achieving a better performance actually, because it has a lower temperature while injected with the same power. So in order to explain this behavior, we can look at how the cases are positioned in terms of thermal conductivity and ceramic quality factor, which is actually the inverse of the loss tangent of the electrics. We can see that actually case 2 and case 3 that has a very similar temperature are having a very close low quality factor, while case 1, which obtained a better results, so colder temperature by 40 degrees compared to case 2 and case 3, it has a very high quality factor. So this allows us to conclude that for this type of components and for this type of constraints in the space environment, the dielectric losses will have a bigger impact on the thermal behavior of the device compared to the thermal conductivity of the ceramics. That's why we suggest that in order to develop a new performant ceramics for our space applications, the effort should be deployed. The emphasis should be put on minimizing their dielectric losses. So at the end, this is the conclusion of this study. We can say that a very simple structure was presented in order to make an analysis in terms of power handling while considering all the multiphysics aspects, but mainly actually electromagnetic and thermal aspects. So here we conclude that the dielectric losses have more impact than the thermal conductivity on the optimization of the power handling performance of the device. And also, in order to validate those studies, future studies need to include non-resonant devices and also devices encountering a bigger surface of contact with metallic and metallic casing and objects, because actually metallic surfaces